Hi everyone, this is Fisher Coder here. Today we're going to through another LeetCode problem 1260, Shift 2D Grid. This is a very interesting problem. It looks straightforward and very easy and simple at first glance, but it really takes some time and tricks or practices to really figure out to make this solution, to make your solution accepted and to make sure your algorithm covers all corner cases. So let's go through the problem description first. Given a 2D grid of size m times n and an integer k, you need to shift the grid k times. That's it. So it further details what does shift grid k times mean. So in one shift operation, element at grid ij becomes at grid I j plus 1. This is one possible how the shift is actually going to work. Second is element at this grid I n minus 1 becomes grid I plus 1 to 0. So to make it better and easier to understand, let's go through this with the help of the graph. Element at ij, for example, let's suppose I equals to 0 and j equals to 0. So grid 0, 0, which is 1, right? It's going to become I 0, j 0. So it's becoming grid 0, 1. So it's becoming 0, 1. It's becoming here. So see, 0, 0 moves to 0, 1. 1 moves to this place, right? That's for the first rule. For the second rule, element at, let's still continue to say I equals to 0, and in this case is 3. And in example 1, n is equal to 3. 3 minus 1 is 2. So 0, 2, 0, 2 is here. Or 0, 0, 2 is here. 0, 2 is here. Is element 3. 0, 2 moves to this place, which is 1, 0. 1, 0, which is this place, right? So number 3 moves from this place to this place, which is at index 0, 2 to 1, 0. That's it, right? This is by going through this example that helps us understand what this grid becomes this grid means. And the last rule is that grid, we actually can already feel some of the rules, how the elements are being shifted, right? So 1 moves to its right, and 3 moves, there is no right on 3. There is nothing, there is no element to the right. 3 is on the boundary. So 3 moves to its next row, the first element of column 0 of its next row, which is this place, right? So let's further continue with the rules. Element at grid n minus 1, n minus 1, and in this example 3 is 3, 3 minus 1 is 2, and grid 2, 2, which is here, 0, 1, 2, 0, 1, 2. So element, we're looking at element 9. So grid 9, the value with the element with value 9 becomes at 0, 0, which means 0 moves to here, which is exactly this case, right? As the example shows. Why? Because 9 is the last element. It's the top. It's the bottom right, which is the last element in this given matrix. There is no place for it to move to the next row, right? There is no next row here. So instead of moving to the next row, it shifts back to the very beginning of this matrix. And where 1 was originally standing, but 1 moved to its next place, which is this one. So after going through this example, we can basically figure out how the shifting really works. Is given number k, we're going to shift every element to its next position, to its next. 1 shifts to 2, 2 shifts to 3, 3 shifts to 4, etc. until 9 shifts back to 1. This is how shifting works, based on the definition of this problem. Okay, with that said, a few key points to note. So with the after going through first example, we kind of have a more clear understanding of what does shift the grid mean, then we can walk through a second example, which is this case. The given original input grid is looking like this, and k equals to 4. K equals to 4, so which means we're going to shift 1, 2, see there are 4 arrows, 1, 2, 3, 4. We're going to shift the grid to the right position 4 times, and this one, the last one, grid over here, is going to be the final output. See, 3, 8, 1, 9, based on our understanding, is going to be 3 is going to be here, 8 is going to be here, 1 is going to be here, 9 is going to be here, right? That's exactly what's happening, and the last one, 13, moves to the top. 13 becomes here, right? So on, so forth, until first shift, second shift, third shift, and then the final fourth shift. And then it becomes like this. So do we need all of these intermediate steps? 0, 1, 2? No, we don't. We can compress all of the intermediate steps into one, which is basically we shifted 4 steps together in one set. We don't need to write a procedure and repeatedly calling this procedure k times. That's not necessary, right? We can compress all of the k steps into one. Looking at this one, we will so this time we will ignore this grid, this grid, this grid, these 3 intermediate grids. We'll just look at the first one and the fourth one, the fifth one, the last one. So say k equals to 4, so we're going to shift total 4 times. So 0, 1, 2, 3. 0, so there are 4 columns in this grid, which means we're going to shift 4 times total. That means 3 is going to end up here. Becomes the first column and second row, right? So the final result shows it here, 3. The same as for 8, 1, 9. They are all being shifted 4 positions to the right, which becomes here, 3, 8, 1, 9, right? And the same case for the rest of the 2 rows. And the last one row, 12, 0, 21, 13, is becoming to the top. So is the final grid looking like 12, 0, 21, 13, right? So this is walking through the second example is what it's telling us. So let's take a further look at example 3. It's going to give us more insight. So the final example is looking at 1, 2, 3 is one row, 4, 5, 6 is second row, 7, 8, 9 is the third row. So look at this. This is a 3 by 3 grid, right? 3 rows and 3 columns. So total it has 9, 3 times 9, 3 times 3 equals to 9. 9 elements total, and it's asking us to k equals to 9, which means this problem is asking us to shift a total of 9 times. So 9 elements total, and k equals to 9. It's asking us to shift 9 times total. What does that mean? Think about that. It basically means all of the elements is going to shift back towards its original position, right? It moves all its way back. 1 becomes 2, 2 becomes 3, 3 becomes 4, etc. until 9 becomes 1. That's after the first shift. Then second shift, 1 becomes at 3's position, 2 becomes at 4's position, right? Until we finish all k iterations, all k shifts, which means it's going to shift back to its very original input position, which is exactly this case, right? It becomes at 1, 2, 3 at first row, 4, 5, 6 at second row, 7, 8, 9 at third row. Very interesting, right? Looks like we got more rules to have discovered. And then another possible case that we can further, k could mean like k could vary from 0, k could equal to 0, or up to 100. But if the grid is like 3 by 3 and k equals to 100, do we need to shift this 3 by 3 grid by 100 times? No, we absolutely not. All we need is actually, we can do a modular, which is k modular m times n. This is all this is all that we need. Let me write it here. This is all the times of shift that we need to perform, because all of if k is greater than m times n, that means we are doing circles, right? We are shifting back and forth, moving the entire grid one whole time, the second whole time, three whole time. We're doing unnecessary operations. In this case, say if k equals 10 and m equals 3 and n equals 3, that means we only need to do, then this one becomes 10 modulo 3 plus 3 is going to be 1. Is that right? So when 10 equals 3 is equivalent to k equals 1. Is that right? So that's going to cut us a lot of unnecessary loops, whole entire cycles, right? So that's another thing that we noted. Then after all of these observations, we can safely draw the algorithm. Is going to be what? Is going to be, we basically shift, the key point for this algorithm to this problem is that we need to calculate the proper index for the next element to be moved. User Rock has posted a very brilliant solution. So as I just said, this problem, there is a common shared technique to apply to such problems, which is often dealing with two-dimensional arrays, which is to flatten. We call it, you can call it whatever you want, but I call it to flatten the 2D array, 2D matrix into an 1D array. How can we do that? Very simple. So this is 2D matrix. It needs two indices. It needs two coordinates to exactly pinpoint where it is on this 2D grid, right? But instead of using 2D, we can use 1D. What we can do is, for example, in this case, we are just looking at example 1, which m is the number of rows, which is 3, n is number of columns, which is also 3, and then, for example, grid 0, 1, which is value is 2. Instead of using 0, 1, what we can use is use 0 times n plus j, which is this one. It's going to be I is 0 times n is 3 plus 1, which turns into 1. So what does this do? It actually it gives us a lot of flexibility and a lot of simplicity as well. So instead of using 0 and 1, this 2D array to denote where the position of this value, we're using only one element, using 1D, one-dimensional coordinate. That's it. So if this is not good enough to help explain what it means, we can use, say, grid 2, 2, which in this case 2, 2 is 0, 1, 2. 0, 1, 2 is 9, right? It's this number. So instead of using that, I times n plus j becomes what? Becomes 2 times 3 plus 2, which is 6 plus 2 equals to 8. So it turns, again, the second example just shows us we turn the 2D array, which requires two elements, x and y, to denote where the position for this element. We're only using this one, 8. That's it. Same as here. So we basically flattened this 2D dimensional matrix into 1D. This is a very common and generic technique that you can learn and apply to a lot of these 2D interview questions. This is number 1. All right, that's number 1. So that's basically a very generic technique that you can learn to apply. And then let's come back to this specific question. where should we start? Use a rock gives a very good example. We can actually, which user am I talking about? I'm talking about this one, user rock, yes. He has implemented a very cool algorithm. What it does is that, where does it start? Where should we start? We should start from this position. For example 1, we should find the position. Basically, we should find the last k position. We start from here. This is the position that's going to be shifted backwards. This is where we should start. For example, 9 shifts back to 1. We start from here because we will create a new. Let's remove all of this. This is draft to explain the algorithm and techniques. And then let's create. We're going to use linked list, the algorithm, integer result. Bear with me just a few seconds. New link. So this is the result. What I was going to show you guys is that this is the result we are building. We are filling out this result with every single element that it should be in its final position, right? We're building this result, this linked list, while we are trying to solve this problem. So we will fill up this new linked list, which is containing another list of integers. So basically, this is the final result. This list, and this list. How do we fill up this final result? We need to find the first element that should be in this position first. So does this one and does this one. That's why we should start from this one. When we iterate through this to the original input, we should find this position and start from here. Okay, so where is that position? Let's write some real code. First, let's use m equals to grid length, which is the number of rows, and n equals to the number of columns. And then we'll use another variable, m times n, which is going to be, this variable is going to be applied pretty often in this entire algorithm because we're going to flatten this array and do the index manipulation, which we're going to use this variable or not. Total might not be a very descriptive name, but we'll just get along with it. And then where do we start? We will have another variable we'll call start. So for example, in example 1, this position is where we should start. How do we put that into all of these variables to put them into in a very generic way, which is to use variables to indicate that? That's going to be, for example here, this is 2, 2. This is the index. How does that apply into the using the generic variables to apply that? That's going to be m times n minus k modulo total. That's why I said we're going to use a lot of this total. How do we get that? So total in this example, we're looking at example 1. Total is 9, and then k is, in this case, is 1. So k modulo 9 equals 1, and then start becomes 9 minus 1. It becomes 8, right? This is the position. So this one line does this magic, which is to flatten these 2D array indices into 1D. 8 is, in the 1D world, that is where 2, 2, where in the 2D world matrix, grid 2, 2, which is 9, where it is positioned at. This is just an example to show what does start mean. And then we'll have a for loop to go through the grid. we'll use I and let I start from here, total plus start. Why do we have total plus start? Because total in this case is 9, start in this case is 8, so 9 plus 8 is 17. Why? Because here we start from this position, which is at index 8, but it has another total 8 elements in front of it prior to it, which we haven't gone through. So we need to plus start so that we can finish iterating through the rest of it. Make sense? Okay, then we're going to calculate which one, after from start, where do we go from here to find its next position, right? In this case it's 9. In another case it's just another element after it. In this case it's 1. Where do we find it? We'll just call that index to be move index. Move index. How do we find that? It's going to be I total, I modular total. So basically, now we're going to find in the 1D world, after we flatten this 2D array, we'll have to find the move index, which is the index in the 1D world that's going to be moved. How do we find it? We're going to use I modular total. In this case, I equals to 8 modular 9, which is 8, which is right here, the last one. And then another common technique is to how do we flip it back? Basically, convert the 1D index into 2D indices, which we're going to use this one. This is another common technique, very generic, that you can apply to other common similar algorithms as well, which is we'll call it. How do we get the 2D indices? We need one row and one column. We'll call it move row, which is the row index. Use integer division n. N is the number of columns. Here, n is the number of columns. And how about columns? Column index. We'll use column. In this case, we're going to use modular n. Say, for example, we'll walk through this using an example. Move index in this case is I is 8. We'll start from 8. 8 modular 9 is 8. So move index is 8. 8 in integer division n equals to 3. So that is 8 divided by 3, which is going to be a 2, right? Integer division, this is 2. And 8 modular 3 is, what's the remainder? It's still 2, right? So you can see which is correct. 8. In 1D index, it's 8. And in 2D indices, it's 2, 2. 0, 1, 2, 0, 1, 2. Row 2 and column 2. Which is correct, right? Remove this. And then so we know where it is. In this case, we're going to just do add, so we know it's this one. Move column. This is how we can really use the value in this given input grid, right? We're going to add this one into the final result, which is result, right? But before we do that, right now, if we do that, it might throw null pointer exception because this one is not initialized. We just initialized the outside container of which is a linked list. So what we need to do is we'll have to check whether this is the first time we encounter this. What that means is that whether we are going through an existing array, which is whether we're going through an existing list, or we finished iterating through this one row, or this one row. We are entering through the second row, the next row, basically. How can we know that? We basically use I minus start and divided by n. Whether this value equals to 0, we know whether we finish iterating through one array and we're going to the next. In this case, if that's true, so for example, we start from start, which is 8. 8 minus 8, which is 0. 0 modulo 3, which is 0, right? Which is true, which means that we are entering through a new array, which is here. We move 9 to the new row, which is the first row of the final output grid. That's why we add a new one. When we go through, when I increments, when I becomes, say, from 8 to 9, then 9 minus 8 becomes 1. 1 modulo 3 equals 1. So it's not equal to 0. So we don't need to go through this. We don't need to initialize a new array list to put it into the final result. Why? Because we are here already. So we just need to move the corresponding correct element into this array because we have an array for this row already. That's it. And then we'll do result. We use linked list, so we can easily use this API pclass, which is helping us to pick the last array in this linked list, and then we call it add. We'll add this one into the result. That's it. Then done. We're done with the algorithm. Let's try to submit and see whether it can be accepted. All right, it does accept it pretty fast. All right, that basically concludes the walkthrough of this algorithm. Again, we learned a few tricks or practices or common ideas that can apply how to flatten a 2D matrix into 1D to help us do the magic, to do the computation, and also the practice how to convert a 1D array back to its original 2D array. These are very common techniques that we can use to apply to other similar 2D matrix problems. If you guys like this video, please do me a thumbs up and also subscribe to our channel, which we are publishing LeetCode tutorials on a daily basis to help fellow LeetCoders better prepare for coding interviews to ace through CS fundamentals. I really appreciate it. If you guys have any comments, feedback, questions, please leave me in the description below. I would really appreciate it. I'll see you guys next time.